At least from a Hollywood sense, you've seen Apollo 13, things go bad when you can't breathe. But beyond rocket engines and oxygen tanks and all that fun, there's the human considerations. Health, which straddles the line between technical and human, of course. Then there's politics. Already we have politics, but that's mostly on the ground. One day, we hope, there's enough people in space that politics will be meaningful in space. And I'm not talking about Skylab meetings, I mean real politics. The economics of space. We're starting to see what people are tentatively calling, finally, the new space age. And more broadly, society, all of us in space together. So, today, I guess I can call it an agenda. It's more of a suggestion list. No one's going to hold anyone to it. We can talk about living in space. We're going to hear from a couple really highly qualified guest speakers who have lived and breathed the space community as far back as the Lincoln goes anyway. I don't know what they did before that. But I guess you'll get to hear a little bit about their perspectives. Then you're going to hear a little bit about us, Space Cooperative, who worked with Cross-Campus Innovate Pasadena to put this all together. And then lastly, we're going to have this thing that we call a jam session. So for those who haven't been here before, a jam session it's kind of like a forum, except much like Congress, it's not going to get anything really done. But unlike Congress, it's going to strive towards something interesting and exciting and something that will eventually bring something good for the human race. We don't quite know what that is, but if we get more people involved in this at a grassroots level like we are now, our hope is that things will get better, generally. So, without further ado, let's hear from our first speakers. We've got Sydney Doe from JPL and Brent Sherwood from JPL as well. And Sydney Doe has a very interesting history, and he came from Sydney, Australia, University of Sydney. Then he came over here to MIT, studied aerospace, and released it's 570-page long thesis that analyzed how to analyze a Martian habitat and all the factors that go into it. And, more in depth than Mark Watney pooping on some potatoes. We're talking about the real math behind it, and it's crazy, it's good stuff. But beyond that, he's also worked on this airbag system for Orion, and now he's working on the Mars Sample Return mission, which will be the follow-up to Mars 2020 rover, over at JPL. And I think you'll hear a little bit more about what he does, what he has to say. Sydney Doe, without further ado.
Hi everyone, how's it going?
All right.
Good. Don't leave you hanging there.
Woo! All right. Well, it's great to see so many people in the audience. Thanks for the great introduction. So tonight I'm going to talk about some of the work that I've been involved with over the last year or so. And it's essentially asking the question, how do you select a landing site for human missions to Mars? We've been talking about sending humans to Mars for 60 or so years now, but we've never really down selected to a specific longitude and latitude on Mars. As you all know, if you're packing to go to Boston during December, it's very different to how you would pack if you were going to Australia during the same time, right? Different climatic conditions, different transportation modes. And in extreme environments, you have all these other considerations to deal with. And I'll get into that somewhat tonight. So I thought I'd share a little bit about those considerations, kind of the ongoing work that's been happening across NASA since about the 2015 timeframe. And yeah, I'd be happy to answer any questions, get your thoughts and suggestions on it afterwards. So as I mentioned, we've been studying how to send humans to Mars for over 60 years now. So is this the laser pointer? Yes. And so it ranges from, so this graph kind of summarizes those main studies. Probably the most seminal original one was from Wernher von Braun, came up with the Mars project. There was a smattering of studies throughout the 60s and 70s when they were asking what do we do beyond Apollo. And then a whole plethora of studies came out in the late 80s onwards when the Space Exploration Initiative was announced by Bush Sr. And so around that period, there was a series of workshops, if you will, for the case of the Mars workshops at University of Colorado in Boulder. And Bob Zubrin's study, Mars Direct, came out, which I'm sure you're all aware of. And then more recently, since that period, NASA has been periodically coming out with these design reference missions or architectures, if you will. They're basically the current state of thinking about what a Mars mission architecture might look like and what technologies might be involved in that. And that's been happening basically up until very recently. However, in all of these studies, a specific landing site on Mars was never really specified or studied in that much detail. And so we're really interested in that now because there's been a lot more interest in Mars over the last 7 or so years, and even from the political level, for example. So in 2010, in the National Authorization Act, it was written that the long-term goal of NASA would be to expand human presence beyond low Earth orbit. This was further refined by a study by the National Academies, which came out in 2014, which stated that the horizon goal for human exploration is Mars. So that's kind of the long-term goal. All of our efforts, whatever path we should take, or should eventually take us to that location. 2014, NASA began a series of studies called the Evolvable Mars Campaign, when they attempted to study in greater detail than had previously been done how you would land humans on Mars, how you would sustain them for prolonged periods of time, what technologies would be involved, and what the roadmap is to develop those technologies from where we are today to a particular point in time that would get us ready to go to Mars. 2015, Journey to Mars report was released, and this at the time was revealing the high-level strategy that NASA had in its mind as to how it would eventually get humans to Mars. And then earlier this year, in this year's Transition Authorization Act, it was stated that the key objective of the US space program will be to achieve human exploration on Mars and beyond. So there's a lot of excitement and interest in Mars. And we've landed stuff on Mars before, as you all know, and we've selected landing sites for missions to Mars. So this year commemorates 20 years of continuous robotic exploration of Mars. We have a slew of orbiters around Mars doing science and doing communications relay for our rovers that are there. This is a map of where we've landed missions on Mars, various locations ranging in latitudes and longitudes. And for each mission, when we select a landing site, it's essentially we define a landing ellipse. And the ellipse contains scientific regions of interest that we want to explore once we land there. And so the size of this ellipse is driven by our capability, our landing accuracy, so the accuracy of the landing system. So when we land something on Mars, the process that we go through to select a landing site essentially starts off with defining the scientific regions of interest that we want to visit, and that's driven by those scientific questions that we want to answer on that mission. And then those scientific regions then define an ellipse that is bounded by the technical capability we have in landing something at that particular site. In addition to considering these scientific objectives, there are engineering constraints. And essentially, the more constraints you incorporate into your landing site selection, the wider your ellipse goes because these uncertainties aggregate. So for example, the temperature and pressure of the atmosphere at the landing location at the time that you're going to land, winds, the altitude of the site, the rockiness of that site, you don't want to land on a rock and have your lander at some weird angle, the slope and lighting conditions. There's also the survival of your rover, so things like the season at the site when you land there, the likelihood of dust storms, the amount of sunlight, which in turn affects the amount of sunlight that gets there, which can affect how much power you get and also the temperature that you need to keep your rover at to survive in that terrain. And also traversability, so how do you traverse between different regions of interest at your site? So that's typically driven by how rocky it is, what the slopes are, and we're really concerned with sand because we've had a bad history with getting stuck in sand. So for human Mars missions, there's a bit more that we need to think about. So I'm going to kind of recap the major activities that have happened over the last few years in trying to better understand the requirements for selecting a human Mars site, landing site for human missions to Mars. So this really began in early 2015 when both the human and science mission directorates at NASA started collaborating and basically formed working groups to better define criteria by which you would select a landing site. So one of the working groups was called the ISRU and Civil Engineering Working Group. So ISRU stands for In-Situ Resource Utilization. And this group was basically tasked with identifying what available resources are there on Mars, what are the requirements for how much of it there is, the quality and how accessible it is, and how can we use these resources to support humans in a sustained presence manner. So we're not just talking about short missions there and coming back, we're talking about continuous sustainment of humans on Mars. At the same time, a science analysis working group was formed to define what the scientific rationale was, or the range of scientific objectives for going to Mars, and then at some point in time, when it's time to go, based on the level of scientific understanding at the time, we would better understand what that specific set of objectives are at that time, and that naturally affects the landing site selection. And then in 2015, an open call went out to the community, and they basically asked for people to propose where they would like their ideal landing site to go. And this culminated in a workshop in October 2015, and from that, basically 47 people proposed where they think the landing site should be. And we further refined the definition of a landing site to be an exploration zone. I'll talk about that in a little bit. So essentially this workshop was the confluence of the engineering constraints coming out of those Evolvable Mars campaign studies that I previously mentioned, and the outputs of these two working groups. Okay, so what is an exploration zone? An exploration zone is a 100-kilometer radius site, and that's constrained to exist within a latitude band of plus minus 50 degrees. And that is really due to thermal constraints. If you go further north, it gets really cold and none of your hardware works. It takes a lot of energy to keep that running. And humans don't like getting too cold also. So this is an example of an exploration zone. Within the exploration zone, you have a habitation site. So that's kind of represented by this black rectangle here. And within that site, if you zoom in, you might have your habitat. It has landing sites, which would be landing zones. So essentially, you can think of an exploration zone as a combination of a spaceport, Kennedy Space Center, if you will, plus regions of interest where you're going to do science and process. So it's a combination of a spaceport and a mining quarry and a scientific research field. So the criteria is that the landing sites are stable, they're low rockiness, and then you also have these regions of interest, and there are two types. There are resource regions of interest, where you have potential feedstocks that we can mine and use, and you have science regions of interest. So a little bit more about the resource regions of interest. The resource that we're most interested in is water on Mars. It's a life support, it's required for life support, and it can be turned into rocket fuel, and it can also be used for radiation shielding, among many other uses. And the requirement that we stated was that it should be in a form, it should be located near the surface, so less than 3 meters, and it is in a form that is mineable by automated systems and located within 1 to 3 kilometers of all our other power and processing infrastructure. And there should be about 100 metric tons of it there. There was also interest in other resources, so these metal and silicon resources, but these aren't as important as water. Water is really key to exploration. And in terms of science, it was really focused on astrobiology, atmospheric science, and geoscience. These are the main themes that drive the Mars exploration program. So just to give you a sense of how big an exploration zone is, so this big circle is an exploration zone. Each of these ellipses, or here's JPL, for example, it's a pixel in our circle. An exploration zone is larger than the state of Hawaii and larger than Gale Crater, where Curiosity is exploring right now. Each of these ellipses represents a landing ellipse based on the landing accuracies of our various rovers. Down here, I'm not sure you can see, but this is Apollo, and this is the Mars Exploration Rovers, an opportunity, and you can see how we've gotten better with our landing accuracy over time. So this is Curiosity, and this is Mars 2020. And this bar represents kind of the lengths at which those missions traversed. So clearly, what we're talking about is about 200 times the scale of the missions that we've been talking about previously in terms of robotic exploration. And the traverses between different regions of interest will be much greater than anything we've done before. So that gives you a sense of the challenge we're talking about here. The outcome of that workshop, 47 exploration candidates, zone candidates were formed, spanning the latitude ranges. If you look into it more, you'll see that different parties or groups came up. A subset of these we visited before, so there are some people in the community who say we should go to where we've already been. Others say we should go to where we haven't been. There's a subset that says we should go underground to protect ourselves from radiation. There's another subset that says that radiation isn't that big of a deal. So, this is, we're at the very start of this whole selection process, and we're also still trying to understand the requirements for what selecting a landing site will be. And I'll talk a little bit about those studies on the next couple slides. So I showed this diagram before. The selection of an exploration zone or landing site is the confluence of engineering constraints, your resource need and availability, and the scientific objectives. So I want to kind of lay out the different decisions and considerations that we need to make when defining each of these aspects, which then allow you to choose your exploration zone. So clearly, I mentioned before, astrobiology, atmospheric science, and geoscience fed into these science objectives. Engineering constraints really come down to how you design your system. What does your habitat look like? What does your life support system look like? Are you recycling your resources, or are you mining them? And how does that interact with your transportation system to get there? These are what I referred to earlier with respect to the landing site safety that we typically go through with our science mission objectives. So safety for landing and both traversing across the terrain. Your system architecture also affects how many resources you need, what type they are. So how much water do you need, how much oxygen do you need, so on and so forth. And that's really driven by things that are more conventionally thought of in the mining world. So what is the type of the feedstock that I need to mine and process that into useful resources? What is the extent of it? So how much of it is it there? What is the quality in which it exists? Can I actually access it? Can I drive a rover or an automated system down there and mine for it? And is it actually extractable? Is it within 3 meters of the surface? Is it within 3 kilometers of the surface? And obviously the science affects the feedstock. So if the range of this presentation, I'm going to kind of talk to better understand these. Also, with this graph, it's interesting to note that the things in black text are the things that we measure. So either things that we want to measure because that delivers value to the whole exploration endeavor, or things that we need to characterize better to inform our selection of our landing site. And the white things are the things that we design or we select. So there's this interaction between needing more knowledge and designing your system at the same time, and they're coupled to each other. Okay, so let's talk about some of the follow-on activities from that 2015 landing site workshop I mentioned. So it's really kind of mining related, trying to understand what the quality of the feedstocks and the raw materials are there for us to mine, and also having a first order design of that mining system. So the outcome of that workshop, 2 major things. There were requests from each of those landing site proposers for more images of their site from some of the instruments on the Mars Reconnaissance Orbiter, which is the satellite orbiting Mars at the moment. And we're currently taking those images for those proposals. And the other thing that came out of the workshop is that we were able to define the 4 most common types of water resource deposits. And you can broadly categorize them as mineral deposits or water ice deposits. And you can subcategorize the minerals as your common regoliths, so the soil that you would see on the average Martian surface. Your phytosilicates, which are basically your clays, and your polyhydrated sulfates, which are your hydrated minerals. And then on your water ice deposit side, it really comes out to being buried glacial ice as kind of the only feasible water stock. And these can be broadly classified as the water ice being at the mid to higher latitudes. And as I mentioned before, we're constrained to plus minus 50. So we can't go anywhere towards the polar region for that. I think this is out of battery. And the mineral deposits are on the lower to mid latitudes. So following that, 5 main studies came out. They're listed here. This study, the NWIP, really focused on better characterizing these feedstocks. Water mining on ice looked at buried glacial ice, and then gypsum mining and processing study focused more on these hydrated minerals. And so one way of kind of summarizing what these studies in red were doing were they were essentially trying to define a reference set of characteristics for how these feedstocks existed naturally on Mars. And then they tried to do a first order design of the system to mine these feedstocks. These blue studies, so the AGU Mars Water Exploration Workshop and the Mars Water Mapping Project are basically aiming to better understand the current distribution of water on Mars and the form in which it naturally exists. So in the first one, we're kind of postulating how it might exist and designing systems to mine them. And in the second one, we're actually looking at orbital data and processing that to try to build better maps. And so I've listed these 5 studies up here. I'll briefly run through them just to give you a sense of the outputs of them. So the NWIP study, this is kind of the seminal study that most people in this community reference. So to provide some background, this is kind of the typical flow of processes in the mining world. You come up with a concept for mining a particular resource that you want, and then you do exploration. So on Earth, this can be through orbital data, through flying over with UAVs, with the sensor packages that you want, and ultimately drilling cores in the ground and trying to characterize the deposit that's under the ground. And after you've done that enough and done some statistical analysis, you have a usable resource deposit, and that's a proven reserve. So you know I can put money on mining in this particular location, and I know that I'll get some return on my investment. So once you define that proven reserve, then you go through the production phase, which consists of mining. So you mine and you get your output of that is your acceptable feedstock, and then you process that into whatever useful end product that you want. And in our case, it's water. And so where we're at the moment is we want to define these proven reserves on Mars. We want to have some confidence as to, at this particular location, there's this reserve, and if we land humans and mining systems there, we can mine that, and we're pretty sure we'll get water out of it. However, there's this kind of chicken and egg problem going on here, in that to define the criteria for what a proven reserve is, we need to have knowledge of what the system to mine it is. And at the same time, to design the system to mine whatever those proven reserves are, you need to have better understanding of what those reserves are. And so that's kind of what this diagram is trying to represent here. And because of this coupling, this chicken and egg problem, we have to move both of them forward at the same time. So both the exploration, so the analysis of the, using the orbital data to better understand the existing form in which water exists, and also the engineering of the mining systems. We have to move them together at the same time. Okay, so another thing that NWIP did was it went through and essentially, defined a reference case for each of those 3, well, there are 2 variants of the normal Martian regolith, 3 forms of hydrated mineral deposits, and then it designed a system to mine that. And essentially it found that for any type of mineral deposit, you have kind of the same basic system. So you dig up some amount of that feedstock, you process it, and that process is essentially you're baking water out of it. So you're adding heat from some local power source. And then once you bake that water out, you get water, you store it in a tank, and then you can do some downstream processes, combine it with Martian CO2, and then you get some rocket fuel. You can also use the water for other things. You can crack it into hydrogen and oxygen and use the oxygen for breathing. But each of these types of feedstocks has a different energy demand required to get the water out of it. And it was found from this study that hydrated minerals, and particularly gypsum, was the minimum mass, minimum energy feedstock. So this is what we want to focus on. And this is the stuff that your drywall at home is made out of, just to give you some context. The other thing that came out of the study is that for each of those feedstocks, so these were the mineral deposits and even for the ice, the people in the study identified what knowledge we need more of to better understand the mineability of that feedstock. And so here in blue, these are the things that we can measure from orbit, and in green are the things that we need to land there and actually touch the surface to better understand. So most of the things, fortunately, about half or more than half of these are things we can measure from orbit, and they typically require imaging to measure kind of the 2D geometry and aerial extent of that, or using spectrometers to measure kind of the mineral makeup of the deposits. When it's green, it's typically requiring that you actually touch the surface, figure out its mechanical hardness and thickness of material above the deposit. So how you're trying to characterize how deep you need to drill to get to it. The second study, mining water ice study, essentially studied this concept called a Rodriguez well, and this has been used in Antarctica since the 1960s. Essentially what you do is you go up to a site where you have high confidence that there is subsurface ice underneath some level of overburden, so stuff above it. You drill so that you have a hole, and you put a hood over the top of it, and then you put a heating element down. It melts the ice, it evaporates, it goes through and goes into a cold trap and condenses back into water. And so this study essentially attempted to quantify the energy requirements of that, and basically concluded that some of the next generation energy systems that are currently being developed at NASA are capable of doing this. We just need to find out if we can land at locations that have this type of water feedstock. So the gypsum study was kind of a follow-up to NWIP. So I mentioned that gypsum was the feedstock of choice. However, in that study, it was assumed that the gypsum appeared in granular format, so small pebbles which are easy to bake and get the water off of. But in reality, we don't actually know what the natural grain size or rock size of gypsum is. So it actually takes energy to crush a rock into a smaller piece and then bake it up. And so the question is, if it naturally occurs in a larger size and it requires additional energy to crush that rock into something smaller, does that still make it more energy efficient than the other types of feedstocks? And so what this study did is we had a researcher from Michigan Tech. He went to different gypsum mining quarries on Earth and explored how they currently mine gypsum. And so this is an image of a quarry from Google Maps, and they use these surface strip miners, if you will. And basically they drive over the surface and they crush it and then feed it into basically a big oven that bakes off the water. So this study looked at kind of what are the natural properties in which gypsum exists and forms on Earth, and how do we mine it on Earth. And it also did an analytical study on what the optimal grain size is when you account for the energy required for crushing. And so this curve, basically the total energy depends on the mechanism by which water is boiled out. So do you get a dry spot on the outside and then it comes in kind of one single nucleation? Or do you get multiple dry spots distributed throughout your rock particle, and then over time as you evaporate, those dry spots combine together and nucleate? And depending on that, your grain size can be in the 1 centimeter range, or the 1 to the -4 meter range, so that's sub-millimeter range. So basically Michigan Tech is taking this work forward, and they're developing actual hardware to test some gypsum mining systems right now. In terms of the water mapping projects, this is kind of an ongoing task, and so basically this started off by bringing together Mars scientists together, and we're basically asking them, what can you do with the data that we already have and that we can get with our existing satellites around Mars? Like, we don't want to spend a lot of money to put more instruments around Mars if we can already process existing data. It turns out there are limitations to what we can infer from existing data, so we will at some point need another dedicated satellite that does the dedicated reconnaissance. But this gives us a first step towards where to target. That we're doing, we're continuing to develop those Mars water maps, as I previously mentioned. We're actually going to hopefully be holding a second human landing site workshop third quarter of next year, and that's open to the public. And then there are ongoing efforts across each of those decision variables that I showed to better characterize that uncertainty in that body of knowledge to ultimately kind of refine this exploration zone concept and help us further evolve our understanding of it. And so that wraps up my talk. Be happy to take any questions, and thanks. So the question was, where is China in relation to us to get into Mars? So in terms of humans, they're mainly focused on the moon in the near term. In terms of Mars, they have proposed, so actually, if I flip back to one of my first slides. Okay, so you probably can't read it here, but they have plans to return samples from Mars somewhere after 2020. They also have plans for having a satellite around Mars, so it's mostly robotic. We haven't really heard much about the details or the schedule, but from what we've heard, it's mostly lunar focused in the near term.
When it comes to the global orbital water survey, are all the necessary instruments already in orbit, or are we waiting for them?
So there are instruments in orbit that can tell us something about the water, but in terms of the quality of data that we would need, it's not good enough. So most of whenever you hear something like if you see an article come out saying that, we've used orbital data and we've detected water, what it's really detecting is water equivalent hydrogen. So it's not actually water. And so it's hydrogen that is likely to be in the form of water, somehow bound with some other stuff that we don't know. So there was a study in 2015, basically looking at what would the ideal next orbiter look like. And the code name we've been using for that is NEMO, so Next Mars Orbiter. So there's a report called the NEXAG report. If you look it up, you'll see kind of the suite of instruments they're talking about. They include synthetic aperture radar, an atmospheric sounder, because we also want to know wind data to support our landing, EDL, entry, descent, landing accuracy predictions, and various other things. Do I have time? Oh. Is this on? Hello? No. Hello? Okay. All right. Any other questions? Yeah.
My question is about the hybrid genome mapping. You said that work was about to get started. Regarding the hybrid and mineral mapping, you said work was about to get started on aggregating those maps and analyzing the data. Who is doing that project?
We have made the selections but have not announced that publicly yet.
Oh, okay.
So stay tuned and you'll find out in the next couple of weeks.
Cool.
Yeah. You got a question on?
It was impressive looking at the energy, just seeing how much gypsum is so much more energy efficient than, it was like order of magnitude difference. For Earth-based gypsum processing, a lot of them are actually recovered from flue gas and such. Have any of the current studies looked at chemical processing, or are they purely focused on mechanical for their operations?
In terms of extracting the gypsum or extracting the water from the
Well, both. Just being able to. The acids tend to typically are a lot more. I'm just curious, if any work has been done in that territory, or they're purely just focused on the mechanical things. It's complicated enough getting it to work on Earth, let alone getting it to work far, far away.
As far as I'm aware, there's some proposals which are proprietary at the moment. They went through the NASA Innovative Advanced Concepts funding system. There's a group that's looking at using microwaves to extract water from gypsum. As far as I'm aware, there's nothing being beyond.
Okay, thanks. That could be some research.
Yeah.
Did you guys look at any of the places where you have a lot of water vapor condensation, like near the equatorial regions, when you've got sublimation of the seasonal cap? Is there enough water there to extract to be useful?
So you're talking about atmospheric-based water and condensing it out of. I'm blinding you there.
Yeah, so like in summertime when the seasonal caps have sublimated away, then they kind of transport to the equator and precipitate out as vapor. So you might have places where you have a lot of water vapor in the atmosphere, but only in particular locations.
So the challenge with that is that to get the rate of water that you need in terms of kilograms per unit of time, you would need a very large system volumetrically to capture that amount of water. So in the MWIP study, they basically ruled out atmospheric sources out of that trade space.
Did you want to ask a question?
So it's an engineering argument.
Just curious, what can you do with 100 metric tons of water? And why do you want that?
Yeah, so it's basically to turn into rocket fuel to get your crew home. That is the largest driver of water. So if you combine water with CO2 in the Savatier process, you get methane and oxygen. Is that right? Yeah. No, methane and water. Anyways, you get methane, and then with water you can crack the hydrogen, the water into hydrogen and oxygen. And so you have oxygen, you have methane, you have hydrogen, which are forms of rocket fuel.
But the 100 metric ton calculation is based mainly on using it to get home.
That was for 5 crews.
Oh.
So we want to send. So an exploration zone is a site in which you don't just visit once; you visit multiple times with multiple crews.
Thanks.
Yeah.
There's so much importance for like not contaminated site,
Yeah.
but then mining, it's exciting.
Yeah.
Geological work.
Yep.
But it sounds like you already have an answer to the question.
I was just wondering what sort of expectations that the geological effects will be on Mars or on wherever we go, and if we're trying to keep from contaminating sites, and what is the process of that?
So there are many thoughts on that, and I'll try to characterize kind of spectrum of thoughts within the community. So obviously there's a discussion we have a lot at NASA. Part of the challenge is that the requirements for planetary protection, which is what you're referring to, have not been defined for human missions. So they've been defined for robotic missions, and we've been following that for ever since we started learning stuff on Mars, even in the Viking era. So in terms of the process, some people have come up with the concept whereby you have quarantine zones. So the way we define the cleanliness of our rover or whatever system to go to whatever site, we call them special regions. And a special region is characterized by if the temperature there rises above a certain level and if there's enough water to support biological activity, so cellular multiplication, if you will. So one of the proposals that has been made is that you essentially, if you're going to do any robotics work in that particular area, obviously humans have to interact with those robots, but you have a kind of quarantine zone that separates kind of the dirty zone where humans are allowed to operate, and then you sterilize your rovers before they go out to that location, do their processing, come back, and then interact with humans and get sterilized every time they go out again. So it's breaking it up into quarantine zones. Fortunately, based on surveys that have been done thus far, the amount of special regions on Mars is relatively low at the moment. But there's also the challenge that when we put humans there, we're going to have systems like nuclear reactors, for example, which create heat, which then induce their own special region now, because the temperature's above a certain level, and if you're you're melting ice and it becomes liquid water, then your water activity is above a certain level. So that's something we're still grappling with, but people are thinking about it a lot.
That's about all the time we got for this round, but
Okay.
more stuff afterwards.
Yep.
Thank you.
I'll be around if you want to chat.
Another round of applause.